Can you hear me? Yeah? Just a quick question at the back. Can you read what's written, or do you need it bigger? Bigger? What about now? People at the back, can you read? Thumbs up if you can read. Thank you. Okay, let's get started. Welcome to Lecture 4. And we're going to pick up today from where we left off last time in lecture. And I like to think about today's lecture really as the lecture on Introduction to Proofs. So we'll talk about concepts that relate to solving systems of linear equations that we've been talking about and we'll continue to build. But really the goal of the lecture today is to develop a style of thinking. And we're going to do that through step-by-step examples that will build the larger story that we're talking about, but try to think critically about the steps that we're going to be taking. So before we get into the material, there's a couple of administrative announcements. First, you've now attended a week of discussions. Please remember that you should go to a discussion on Monday and on Wednesday. The material is different. And lecture will assume that you've been to discussion. Homework will assume that you've been to discussion. So it's in your best interest to go. We saw that some time slots had a lot of people trying to get into one section. I think one particular discussion section had upwards of 90 people in the room, whereas other rooms had maybe 10 or 12 people only. So what we've tried to do is we've tried to add a discussion section from 1 to 2 p.m., which was one of the most crowded times. And one of the 5 p.m. sections has been canceled. So if you were in a crowded 1 to 2 p.m. section, or if you would like to go to a section from 1 to 2 p.m., there's a new section because it seems like that's a time that's convenient for most people's schedules. So please try to go to that section. The 5 p.m. section is canceled. So the updates are on Piazza and on the website. Please check and go to the right section on, I guess, tomorrow, Wednesday. If we see that there are certain sections that keep having a large population, we will try our best to rebalance them. But we don't have that much control over the room reservation system. This comes from campus, so we may or may not be able to actually do this. Okay, the second thing I wanted to say is about lecture today. We're going to be doing a series of proofs, and we're going to be introducing a lot of new mathematical definitions. And a lot of what I'm hoping you will get out of the lecture is in the process of thinking that we are going to be going through. So there'll be a lot that'll be said that won't necessarily be written down. And so I ask that you try not to distract yourselves with technology. Try to stay away from social media, especially for this particular lecture. In general, we recommend also that, don't bring your laptop to class, or don't, try to take, if you're taking notes on an iPad or something, that's great, but, try to, say, okay, promise yourself, I'm not going to check my email, I'm not going to open Facebook, whatever it is. Hopefully this will be the best for your learning. That said, if lecture turns out to be really boring and you really want to check Facebook, try to do it in a way that doesn't really bother your neighbor if they want to concentrate. Okay, so today I want to start off with going back to basically span that we talked about last time. And then I'm going to introduce these ideas of linear dependence and independence. And what was the definition of span that we talked about last time? We talked about the span of a matrix. And the span of a matrix, or a span necessarily of a set of vectors, A1, A2, AN. We will use these somewhat interchangeably. Here, if I can think of A as being the matrix that's made up by these column vectors. So remember, each column vector is long. It's a column. And if I stack them together, I get a matrix. So I can think of the span of A, or I can think of the span of the columns that make up A. These are exactly the same thing. We will also use words, and these will become more clear in the following lectures, but I just wanted to introduce you to some jargon. So jargon alert. Is span of A is equal to really range of A is equal to column, C-O-L-U-M-N, column space of A. These are all different things. We'll talk more about where these different names come from, but I just wanted to let you know, in case you come across these words in different contexts, they all mean the same thing. And what do we mean by span? The span is really the set of all vectors V that can be written as a linear combination of A1, A2, all the way up to AN. Right, this is how we define this. And we also said that, based on what we know about systems of linear equations, this is basically the set of all vectors B. B is a dummy variable, V, B, it doesn't matter what I use, such that AX equal to B has a solution. And why are these two things equivalent? It's because we remember from last time that we saw that A times X is basically taking linear combinations of the columns that make up A, right? Does everyone remember that discussion from last time? So this is basically representing linear combinations of columns of A. And I wanted to rewrite this definition for you just in another notation so that you get to see this notation. AN. This span, which is the same thing that I've written here, I'm writing the same thing three different ways. This is equal to the following set. This is what is called the sigma notation, to 1 to n CI such that Ci belongs to R. And this symbol, this is the Greek letter sigma. This might be the first time you're seeing this notation. What does this mean? If I write sigma and I have an index I going from 1 to n, and I write this index I here, this basically is equal to 1 plus 2 plus all the way up to n. So I'm saying I start at I equal to 1, and I keep incrementing by 1 until I reach the number that's at the top of the sigma notation, and I add them up all together. That's what this notation means. So here, when I say sigma ci ai, this thing is basically equal to, is this blue color visible? Can people read it? Yeah? Okay. This is equal to C1 times A1 plus C2 times A2 all the way up to Cn An. And what does Ci belongs to R mean? Ci belongs to R is just saying that all these Ci's are real numbers. So we will end up using this notation occasionally in class. There's nothing about it. It's just a shorthand way of writing out this expression instead of writing this long expression with dots in it. Is this notation clear? Are there any questions on what this sigma notation means? Some people you might hear this called sigma notation. Because this symbol is basically the Greek letter sigma. Any questions about this? Okay, great. So, this basically is just a way of saying, oh, let us look at all the linear combinations of these columns, or let us look at all of these vectors such that Ax equal to B has a solution. This is just another way of writing out a linear combination of the vectors A1, A2, An. Okay, so we have this. I'm going to move this now here. Let's see if these 2 document cameras work this time. And now let's do some examples. We did one last time, but it was kind of fast. So let's look at the span of, let's say, 1, 1, and 1, or minus 1, minus 1. What is the span of 1, 1, and 1, minus 1? If I was to draw out a picture, what are these vectors like? If I plot them in R2, remember we talked about R2 as basically the set of all like tuples of real numbers. So 1, 1 is this vector here. Minus 1, minus 1 is this vector here. And we're looking at all linear combinations of these. And remember, these linear combinations, these coefficients here, these can be negative. Right? So now, basically this means I can walk in this direction as much as I want, either forward steps or negative steps. I can take steps forward or backward. And I can walk in this other direction as much as I want. So where can I go using these 2 vectors? It's a line, right? I can go anywhere along this line. And so the span of this, if I was to write this now mathematically, I would write this as the following set. I would write this as the set of all vectors alpha, alpha, basically where the first component is equal to the second component, and alpha is a real number. So this basically means that I can choose any real valued alpha, and I can get to that vector, right? This set contains all of those such vectors. Let's look at another example. Example 1, example 2. Span of 1, 1, and 1 minus 1. So now here, I have one vector is the black vector that we've already drawn. And what is 1 minus 1? 1 minus 1 is this orange vector. So if I wanted to, let's say, get to some arbitrary point here, can I get to that point walking just along 1, 1 and 1 minus 1? Intuitively, there's a sense in which we all feel yes, right? Is it obvious how, like, let's say this was, what does this look like? This looks like, let's say this is 4, 2, right? You'd have to do some calculations to figure out how many steps to take exactly in each direction, right? We can't immediately just look at the picture and tell. But it seems like you could get to 4, 2. What about, could you get to somewhere in this quadrant? Here? Here? You could probably get to all of these points. So what would we like to be able to say about the span of 1, 1 and 1 minus 1? R2. We want to be able to say that the span is R2. And what we're going to do now is actually prove this. We have a sense, we have some proof by examples, right? We can put in 4, 2 and try to compute. But we want to try and do this rigorously. So we want to say theorem, this is the first theorem you're doing in this class, span of 1, 1, 1 minus 1 is equal to R2. So take a minute and maybe think about how would you prove such a thing? What does it even mean to prove such a thing? And if we can just see, like, can't you just say, well, you can get to this point, and you can get to this point, and you can just get to this point? It seems like there's not even something to show here, right? This is an example of a simple thing, but we need to go through it step by step. So if you had to rigorously prove this, maybe think about how you might try to do this. Feel free to talk to your neighbors, discuss, and see what steps seem natural and what steps seem unnatural. So I want to give you some time to think about it on your own. Talk to your neighbors, take a break, whatever you want. Try to make sure people don't feel left out. So look to your left and look to your right. Okay, how many people think they have some ideas on how you could try to do this? How many people are not even sure what the question I'm asking is? Yeah. It's not clear, right? How do you prove something? What does it mean to prove something? We've never talked about it in this class before, and that's what I'm hoping to do in today's class. But is there someone who wants to share one of their ideas? Yeah.
Could you say that these two vectors are somewhat of a linear combination of two vectors that you know? spans R2?
The idea was, could you say that these two vectors are a linear combination of two other vectors that you know span R2? That's a very interesting and valid proof approach. So if you could somehow say that, these two vectors can be represented as a linear combination of something else, and those two represent all of R2, then you can kind of do a two-step-by-step procedure by which you can get the required linear combinations. The challenge is that we have not yet proven that any vectors span R2. So from the perspective of building up from first principles, we can't fully do that. But it is a perfectly valid and great idea for a proof approach. Someone at the back, yeah, all the way there.
Would it be helpful to first describe R2?
Great idea. Would it be helpful to first describe R2? That is one of the steps we're going to take. Yep. How about over there? Yeah.
I thought maybe if I add V1 and V2, you can get, let's say, 2 and then 0. And then if you add V1 and negative V2, you would get 0, 2.
Uh-huh.
And now you can make literally any vector ever.
Yep, that's a very good idea. It's very related to the idea about, can you find a linear combination that spans the space and then use that as a decomposition. So that's a really good idea. Okay, last idea at the back over there.
I would say pick an arbitrary point in R2, call it A, B, and then solve for what the combination of these vectors gives you A and B. And then because A and B are real numbers.
Yep, that's a great idea, and that's part of the idea that we're going to follow in doing this together. So we're going to try to follow that idea as well as the idea that suggests let's try and describe R2. So the important thing to notice is that everyone had a slightly different approach and a different way of proving things. And this is good. Proofs are about creativity, but they're also about step-by-step planning and procedure. So having different ways of doing things is a very good thing. And it's not necessary that two people will come up with the same proof for a particular concept. So keep these ideas coming. So how we're going to go about doing this pen is not working, is we want to show that these two sets are equal, right? So in the span of 1, 1 and 1 minus 1, there's a bunch of vectors. And in R2, there's a bunch of vectors. So let's ask first the question, can span of 1, 1 and 1 minus 1 be bigger than R2? Right? If we want to say that these two are equal, then everything in here should be in here, and everything in here should be in here, right? None of these sets should be bigger than the other. So what is the span of this, right? So let's say consider some vector v. Which is a linear combination of our two candidate vectors, right? So how do you represent a linear combination? Let's take some constants. Let's call them alpha times the first vector plus beta times the second vector. Right? This is a linear combination of our two vectors. What is that going to give you? Well, I can add the components up. This is going to be alpha plus beta and alpha minus beta. Right? Is this now an element of R2? Right? Why is this an element of R2? Why does this belong to R2? Because both components are real numbers, right? And our definition of R2 is all those vectors where each component is a real number. So we've seen that if you have a linear combination of these two guys, well, they're a vector that belongs to R2, right? This is a step that at some level, once you start doing lots and lots and lots of proofs, is a simple step, and you might, choose to not write it out as explicitly. But right now, because we're learning to do proofs, we're going to write every single step out super explicitly. So what this means is that if your vector v belongs to your span of these guys, then v belongs to R2. Right? So we've shown that basically the span cannot be bigger than R2. What's the other thing we now have to show to complete our proof? We want to show equality, right? We have to show that it's no less than, or we have to show that basically every single vector in R2 is part of the span, right? We've shown every single vector in the span is part of R2. Now we have to show every single vector in R2 can be represented as a linear combination. Everyone clear on the second part? If you're not clear, ask your neighbor. If both of you can't figure it out, please raise your hand and let me know. Ask questions. So the second part is, can any vector in R2 be represented as a linear combination of 1, 1, and 1, minus 1. So here we're starting with the opposite vector, right? Here we started with the vector in the span. Start with v in span. Now we want to start with some u belonging to R2. You see how we're starting on the other side? So what's a general u that is in R2? Well, let's consider u, which is u1, u2, and u1, u2, both are real numbers. Right? This is a general vector. So now, what is the question? Can we find alpha beta such that alpha times 1, 1 plus beta times 1 minus 1 is equal to u1, u2. And we have to be able to do this for any u1, u2, right? We're not making any assumptions on u1, u2. We're not saying u1, u2 is of the form alpha, alpha. We're not saying it's of the form alpha minus alpha, right? u1 and u2 are arbitrary real numbers. So this is where we want to now start to use some of the tools that we've built up. So we want to figure out if u1, u2 can be represented in this format. I want to take this and manipulate a little bit. So this is kind of our beginning. Oops, thank you. This is our beginning point. This is our end point. And we're going to kind of try some manipulations to see how we can get from beginning to end. So you're here. Okay. So I have alpha times 1, 1 plus beta times 1 minus 1. These are linear combinations of columns. We have now a way of representing this compactly, right, using matrices. So I can write this just as 1, 1 times alpha plus 1 minus 1 times beta. I did nothing. I just rewrote the multiplication. The scalar can go on either side of the vector. But now, it's basically this vector scaled by this constant, and then this vector scaled by this constant. I can write this out as a matrix. 1, 1, 1 minus 1. And make alpha beta into a vector. Right? And so now the question is, does 1, 1, 1 minus 1 alpha beta is equal to u1, u2 have a solution? Right? If this has a solution, then that means I can find alpha beta to get u1, u2 as a linear combination. Right? This is just rewriting essentially the definition of span. I'm doing it out in a slightly longer way, just so that you can get used to the definition of span. There are other ways to do this proof. It's not the only way. But now, what are you in a situation where you know like basically one thing for solving systems of linear equations, right? Gaussian elimination. So why don't you quickly do Gaussian elimination? I'll do it on the side here as well. And see what you get. So this is known. This is known. This guy is unknown. And so I can write this now as 1, 1, 1 minus 1. u1, u2. I'm just going to do the row operation first. So r2 minus r1 gives me 1, 1, u1, 0 minus 2, u2 minus u1. Then r2 divided by minus 2 gives me 1, 1, u1, 0, 1, u1 minus u2 divided by 2. And then I do the back substitution step. So this gives me that the second component, that beta is equal to u1 minus u2 over 2. I do back substitution to basically get this 1, 0, 0, 1 here. And here I get u1 plus u2 by 2. And here I get u1 minus u2 by 2. So this means that I have alpha is equal to u1 plus u2 by 2. Beta is equal to u1 minus u2 by 2. Yeah, question?
I think on the third step in Gaussian elimination, you wrote u1 minus u2. Oh, wait. Never mind. I thought there was an arithmetic there, but my bad.
Okay. No worries. Good. It's good to, like, it's very, very easy to make algebra mistakes, right? So good to catch these things. Yeah. So we saw some examples last time that showed that just by looking at for whether there's a row of zeros doesn't always necessarily give you the right answer, right? So you actually have to go through the entire procedure. So that approach could work, but it might not work. In this case, you're not going to get a row of all zeros, but in the case where you had a separate situation, you might. Let's talk about it offline. Yeah. What is the objective of the first part of the proof? Which part? This part? Before we did the u and u2 stuff. That's a great question. What is the point of this part of the proof, right? So when you want to show two things are equal, two sets are equal, you have to show every member of the first set is a member of the second set. In this case, it's simple to see that if you take a linear combination of the two vectors, they belong to R2. But because we're learning how to do a proof, it's important to do that first step out. Like once you're taking grad classes, or even when you're taking classes like 70, you might not do this. But the goal of 16A is to help prepare you for classes like 70, where you're going to be expected to do more advanced proofs. So this is like kind of the first very, very ease into proofs type of problem. Okay, so we're here. We basically have alpha, beta, and we've figured them out. So now this means that for all U1, U2, which means all U, we can find alpha, beta. And basically, this means that all U can be written as a linear combination. Basically, you can say QED, which is basically Latin for what was to be shown. You started out by saying that you wanted to show that all vectors in R can be written as a linear combination. And what you have done here, this style of proof, is what is called a constructive proof. You ask the question, can every vector in R2 be expressed as a linear combination? And the way you answered that was by finding that linear combination. You found exactly those numbers. Right? It's possible to prove things without necessarily constructing an example, and we'll see an example of a proof like that. But what you did here, it's important to remember, is that you did a constructive proof. Okay. Yes, question? The question was, can you just prove that the vectors are linearly independent? We will eventually get to learning about linear independence and dependence, but we haven't even defined those things yet, right? So when you're doing a proof, you have to know what is in your scope, what is in your toolbox, and what isn't. And because none of those are in scope, because we're proving things from first principles, that would not be necessarily a valid approach that we could do right now. But again, if you're taking an advanced class, once you've learned that in the class, you're welcome to do things like that. But we haven't learned that yet, so that wouldn't be a valid way of proving it right now. Yes, at the back. How do I know that that linear combination has no solutions? So I basically set this up as alpha and beta are the coefficients of the linear combination. Right? Alpha and beta are basically alpha times the first vector plus beta times this vector gives me vector u. And I'm solving it using Gaussian elimination. And by Gaussian elimination, I'm constructing the example. So I know that there isn't a solution because I constructed it. Yeah. We could have two equations and two unknowns and have infinitely many solutions or no solutions. Two equations, two unknowns doesn't guarantee that, right? And we're going to see more of how and where. Like, this is a great lead-in to what I want to talk about next. So, let me move on. I'm sorry? What has a solution? This equation has a solution because I computed it. This is the equation, right? Alpha, beta are my unknowns. U1, U2 is a vector that is given to me. I'm writing it in terms of symbols. But I know exactly what U1, U2 is, right? So it's important to remember, this is known, these guys are unknown. Alpha, beta are unknown. Good question. Okay. So this leads me to moving to the next part, which is, remember last time we talked about when we have our experiment, we have some object. Oh, thank you. We have our object, which is X, and we're doing our imaging experiment, right? And our imaging experiment is represented by this matrix A, which is taking linear combinations of the pixels of the object. And this gives us our measurement. This is the tomography example. And our question was, how do I know that my design of my MRI machine is good from the get-go? Or at least, how do I know that it's not bad from the get-go? And we said last time that we're going to answer that question in today's lecture. And for that, I want to basically introduce a definition. And this definition is linear dependence. We say a set of vectors, A1, A2, all the way up to AN, are said to be linearly dependent if one of the vectors can be written as a linear combination of the others. So what does this mean? Effectively, it's saying if one of your vectors in your set is in the span of all of the other vectors in your set, then your entire set is said to be linearly dependent. Linearly dependent meaning you take some linear combination of some of them and it gives you the other one. And linear dependence is something that's going to, show up a lot. So for example, if you have the set, let's say 1, 1, and 2, 2. Is this set of vectors linearly dependent? Yes, this is linearly dependent because 2 times 1, 1 gives you 2, 2. Okay. What about 1, 1, 1 and 1, 2, 3? Are these linearly dependent? No, right? You cannot do this. This is not linearly dependent, or, you could also write this as linearly independent. What about 1, 1, minus 1, 1, and 2, 3? Is this set of vectors linearly dependent or linearly independent? Okay, I'm getting different answers now. So take a minute, figure it out, talk to your neighbors. So do we have some kind of consensus? What did we talk about? What did we look at for these two vectors, 1, 1 and 1, minus 1? Or minus 1, 1, which are just the same vector. What is the span of these? R2. Can 2, 3 be written as a linear combination of 1, 1 and minus 1, 1? Yes. So is this set of vectors linearly dependent or independent? Dependent, right? Okay, good. So this is linearly dependent. Okay, so we have some examples. Now let's get really to the meat of the lecture. which is now we're going to actually prove a theorem that connects linear dependence and independence to systems of linear equations. We say if the columns of A are linearly dependent, then AX equal to B does not have a unique solution. This is the second theorem that we want to prove today. And for this, actually, so I wrote out, I'll post this later, but I want to kind of try and use these tips for writing out proofs that we can think about while going through this process. So there's two learning objectives that I want to achieve in going through this proof. The first one is proving to you that this is true, right? Because, hey, this is great, right? If we set up our imaging machine and it turns out that the measurements it are taking gives us linearly dependent columns, we know it's a failed endeavor, right? We know we should go back to the drawing board because we know that we're not going to get a unique solution. So that's one part of the learning objectives. But the other thing is I want to try and use this to think about constructively how can we step by step build up a proof. So this is a pretty complex thing to prove. It's more complex than proving that the span of the set that we just discussed is exactly R2. So when you're trying to do a proof, there's a couple of things that I always recommend. And the first thing is that you want to try and write out kind of the beginning part of the proof and the end part of the proof explicitly. So here, let's look at this statement. So we have if. We have an if and we have a then, right? So if this statement is true, then we want to prove this second part is true. One of the things I see students confuse a lot is, accidentally trying to show that the second part of the statement implies the first part of the statement. So when you're reading a statement, look at the implication. It says, if something is true, then something else is true. So you want to show this part, this clause implies this other clause. So this is the kind of proof where you have a P implies Q. So P is this first statement, and Q is this second statement. So look at the direction of the implication, right? That's what this is saying. Look at the direction of the implication, and then write out what the two clauses are separately. So here, you want to basically say if the columns of A are linearly dependent. So let's write out this proof. So the beginning. So what does it mean to have the columns of A linearly dependent? Well, let's say A is given by A1, A2, AN. These are the columns of A. We know that for some AI, there is some column AI, we don't know which one, but the one of them is equal to a linear combination of the other ones, right? So I'm writing out this definition of columns are linearly dependent in this mathematical notation, right? So I'm saying for some column AI, it is a linear combination of the other columns. And here in this linear combination, I want to make sure that I don't write AI equal to AI, right? That's not a valid linear combination. So I'm specifying that I cannot use any columns equal to the ith column, but I can use all of the other columns, right? Going from 1 to n, except for the one where j is equal to I. Is this notation clear to everyone? Yeah, question?
So you're saying, for some column AI, this sigma notation is true, but if all the columns are linearly dependent, shouldn't it be for all columns AI?
Good question. So the question is, why are we choosing just one AI? I'm saying it's true for some AI and not true for all of the AIs. Let's go back to the definition of linear dependence. It says, the definition says, if one of the vectors. So we might not have this be true for all of the vectors, but only one. Sometimes it'll be true that there'll be multiple linear combinations, but other times it might not be. So you have only one, so you can only assume that one. Yeah, question?
Question about syntax for sigma notation for the statement on the bottom. Does the order of those two statements matter?
No, it does not matter. Good question. Okay. So we have this beginning statement, and what is the end statement that we want to try and get to? We want to show that AX equal to B does not have a unique solution, right? This is a bit harder to immediately mathematize, right? What do we know how to mathematize? You don't know how to say something is not a solution. But what we're going to try and do here is we're going to try and do a proof by contradiction, which is a different style of proof from the style of proof we just did. So here we're going to say, assume, if possible, that AX equal to B has a unique solution. Let X star be this solution. And now the proof approach that we're going to try and take is we're going to say, well, let's try and go from here to here, but show that, what we're assuming here is wrong. Let's arrive at a contradiction. So whenever you have some kind of complex proof like this, like dealing with these sigma notations, dealing with n columns all at once, this can sometimes be quite complicated and can distract you from thinking about the core ideas in the proof. So I always recommend is the first thing you should try is try out basically a small, simple example. So here today, let's try and do this just for the context of A is a 3 by 3 matrix. So let's do a simple example. So let's say A is equal to just A1, A2, A3. And is 3 by 3. And furthermore, let us say we can write this now. We want to write this condition of linear dependence in our 3 by 3 context. So now we have this question, right? Is A1 dependent on A2 and A3? Or is A2 dependent on A1 and A3? How do we figure this out? So one option is to do cases, to say, well, let's first assume that A1 is dependent on A2 and A3. Right? All we know is that one of them is dependent. We don't know which one. So let's pick one. So let's say, assume A1 is equal to basically some C2 times A2 plus C3 times A3. And remember, we will check this for A1, do for A1. must also check for A2 and A3. And what we'll find out, we'll do these steps and we'll find out that actually the procedure that we would go through for A2 and A3 would be very, very similar to the procedure that we would go through assuming A1 has a dependence. And so we'll introduce this notion of what we call without loss of generality. But I want to come back to that at the end of the proof. Here I just want to say, let's for now assume that A1 is what is dependent on A2 and A3. So now that we are here, let me pause and give you a chance to try and play with this a little bit yourself. So what do we have here? We have a simple example. We're doing this just in the context of the 3x3 case. We're assuming A1 is a linear combination of the other two columns. And we want to arrive at a contradiction to X star being the unique solution. So the next step in kind of our standard way of doing proofs is to try to manipulate basically the beginning side and the ending side or any combinations to see if you can get to where you want to go. The important thing is to take small steps, and every time you make a transformation, justify why you're doing that transformation. Write it out. Be explicit. So take a chance to, take a few minutes to do it on your own, talk to your neighbor, see what you can come up with. Try to talk to new people. Make sure that, people aren't left out. Be very, very inclusive. How many people want another minute for discussion? How many people are ready to move on? Okay, it's about equal, so I'll give you a minute. Okay, everyone stop talking. Okay, we can move on if people are ready to move on. So, when I see something like this, what is my first thought? Right? To me, right now, it's not at all clear how to go from this, like this is something about the columns, and I want to now prove something about the matrix, right? I have columns and I have matrix. So I somehow want to get these columns to reconfigure back to looking like a matrix, right? Because here on this side, I have A times X equal to B. So all the columns are stacked together in this matrix form. So how can we make this look like a matrix? Yes, question? Oh, sure, why not? Yep. So basically, the next step that I want to do is, I think about it a little bit differently, but that's exactly, every one of us will think about it differently. That's exactly the right way. So I want to make these things look like a matrix. So I'm going to look at this. So I'm going to look at the left-hand side of this. And what is A1 in terms of, can I write A1 as a matrix vector product? If I take the matrix A, which is equal to A1, A2, A3, and I multiply it by the vector 1, 0, 0, what do I get out? A1. So this left-hand side is basically A times this vector, right? 1, 0, 0. Does everyone see that? What about the right-hand side? Can I write the right-hand side also as a matrix vector product? I can write A1, A2, A3 times, what would I want to write? How much, I'm scaling, so the three columns are A1, A2, A3. What is A1 being scaled by on the right-hand side? 0. A2 is being scaled by C2, and A3 is being scaled by C3, right? So this is basically A times 0, C2, C3. Maybe, okay, I'll try and write on this sheet of paper so you can see everything in one. Okay, so now I have both sides of this equation that are represented by A. So I have basically A times 1, 0, 0 equal to A times 0, C2, C3. Right? I can now reorganize this to say that A times 0, C2, C3 minus A times 1, 0, 0 is equal to 0. Right? Just reorganized. Remember, take small steps. Try not to do lots of things at once. It often leads to algebra mistakes or mistaken logic on exams. I recommend against it. This implies, now I can write this as basically A times minus 1 C2 C3 equal to 0. Right? So I have A times some vector equal to 0. What else have we assumed? We have assumed that X star is a solution of AX equal to B. So what this means is that I have A times X star is equal to B. Right? by our assumption, we have A times X star equal to B. Okay, so what do you want to do now? What do we want to get a contradiction to? We have said that X star is the unique solution, right? We want to somehow say that this is false. We want to arrive at a contradiction. So what's one way to say that X star is not the unique solution? Multiply it by 0. Multiplying it by 0 would just give us a 0, right? We wouldn't necessarily, but you're on the right track. You're thinking exactly in the right way. You want to somehow use this 0, right? There's a 0 that we've created here. And we can add zeros to things without creating a problem. So if I can somehow create a second solution, if I can give you another solution, X double star, that is not equal to X star, but is also a solution, do we have our contradiction? Yeah? Question? If everything inside this vector were multiplied by a constant, it would still be 0, yes. Yes, but we don't need to use that right now. Yeah. Yes, white t-shirt. Yep, that's exactly what we're going to try and do. There was a purple t-shirt or a red t-shirt question also right there. Yeah, you? No? Good? Okay. Okay. So how do we create our new solution? Let's consider A times X star plus 0 equal to B. Right? If A times X star equal to B, A times X star plus 0 is also equal to B. Nothing has changed. But what is 0 equal to? It's A times this vector. So I have A times X star plus A times minus 1 C2 C3 equal to B. This means that A times X star plus minus 1 C2 C3 is equal to B. I'm going to call this vector X double star. This implies A times X double star is equal to B. So what does this mean? X star is not unique. We just produced a second solution, right? What is the one thing we have to check to make sure that X star, that we can go forward? What if X star and X double star were equal? Would we get our proof wouldn't hold, right? This would not be a contradiction. So how do we know that X star and X double star are not equal? This vector that we're adding is not all zeros, right? So now what we have to do, so now we have found X double star also a solution. X double star does not equal X star because X double star minus X star is equal to minus 1 C2 C3. And why do we know that minus 1 C2 C3 is not equal to 0? C2 and C3 could be 0, right? But we have this minus 1 here, and we know that minus 1 is definitely not 0. This is not equal to 0. So we have to do this check. Check. This implies X star is not the unique solution. This is a contradiction. Which means that we are done. Yeah?
I lost track of where the check came from. Why do we know that x double star minus x star?
Great question. So, excellent. Thank you for asking. So, we're over here. We've added a times x star plus 0 equal to b. Now we have a, we pulled the a out, so we have a times x star plus this vector equal to b. And x double star we're defining to be equal to x star plus minus 1 c2 c3. Right? We're defining this here. This definition is hidden here, but now it's also called out over here. Excellent question. Everyone with me here? And now we want to check to make sure that, well, we created a second solution, but how do I know that the second solution isn't just x star plus 0? Right? That's a trick way of creating a second solution. That's not actually a different solution. Well, we can check that the difference between them is not 0. That's why we know. Do you see how this style and flavor of proof and way of thinking is different from the first proof that we did, where we created the example? And this was a different flavor of proof. So it's something to keep in mind. Any other questions? Like, this is complex. Yes, black shirt. Great question. How does this prove this works for all matrices, not just 3 by 3s? We haven't proven that yet. We were just doing the simple example part. So what would be the next step that you would do? You would do this out basically for the larger setup. But you now know exactly what you would do, right? So what would be the thing that you would want to do? So if I knew if I said AI was equal to sigma I not equal to j, j equal to 1 to n, cj, aj. What was the key step here? This was the key step, right? So I know I can rewrite this out as a times 0, 0, except there's a 1 in the ith position. 1 in ith position. And the right-hand side, we know, is C1, C2, except there's a 0 in ith position. Right? Instead of 3, now if you had a setup where you had n columns, you would basically get this exact same thing, but now instead of having the 0 in the first position, you would have it in the general position. In fact, even for the 3 by 3 case, right, we've only done the one case where you assume that A1 is a linear combination of A2 and A3. What about the other two cases? Here is where I want to introduce this idea of what we say without loss of generality. What this means is that I have this symmetry between A1, A2, A3. If I assume A1 is a linear combination of A2, A3 and go through the proof, mechanistically I can basically do the same thing for all of the other cases. So that's why you say without any loss of generality. Like we're doing a specific case, but it applies to the general case. That's what without loss of generality means. And so here, we did this one assumption. In the n by n case, you would say without loss of generality, let AI be representable as a linear combination of the remainder. You would have these two steps. You would have this step, and you would basically follow through the similar steps. The reason to do it out in 3 by 3 is starting to think about this, large thing with keeping track of these indices and i's and j's is super complicated, right? It's easy to get lost. So we basically do it out as a 3 by 3 example first and then do the general example. Great question. Does everyone see how we could use the 3 by 3 example to kind of build a proof for the larger case? Yeah? Thumbs up if you kind of do, thumbs down if you don't. Okay. Okay. Yeah, blue t-shirt. We haven't talked about converses yet, and we will eventually, but it is not. But yeah. It is important to keep in mind, this question is basically related to implications, right? What we're saying is that if the columns of A are linearly dependent, then AX minus B does not have a unique solution. This is not saying that if AX minus B does not have a unique solution, then the columns of A are linearly dependent. That's a different direction, and that's not what we have proven. Other questions? Yes, great t-shirt. Hey, I'm going to ask people to keep their voices down just because we have a couple of more minutes and I really want to answer people's questions if they have questions. Great question. The question is, if the columns are linearly independent, then can you prove that you have a unique solution? We will get to this in the next lecture, but this will be true only for square systems. We will not be able to prove this generally, because it isn't true. Good question. Yes, red blouse. Without loss of generality will apply in general. I can barely hear you, so let's talk after class. Hey, folks, please be polite to your other students, to your fellow students who are trying to ask questions. If you want to leave, that's fine, but be respectful of the people who have questions. Any other questions? Yeah.
So this A times the vector 0, 0, 1, 0, 0, was the purpose of you writing that to prove that no matter the dimensions, it's still true?
Yes. The question was, why am I writing this generally with the dots and the zeros? And was the point of that to say that regardless of the dimension, this holds true? And the answer is basically yes. I want to conceptually say that no matter what, I'm going to be able to come up with a vector that is of this form, that is A times C1, C2, all the way up to Ci minus 1, 0 in the ith position, Ci plus 1, all the way up to Cn. This is equal to 0. So this is the parallel of, sorry, I want to have a minus 1 here. This is a parallel of this vector, where the minus 1, instead of being in the first position, is now in the ith position. And here it doesn't matter how many columns you have. Yeah? How do you prove that something happens without loss of generality? That is a great question. Usually you prove it by symmetries. The first couple of times you're doing proofs, it might be worth it to convince yourself by doing out the case where A2 is dependent on the other guys. But quickly you will start to see that basically any time that there is relabeling is allowed, without loss of generality holds. That's the short answer to that question. Yes? Yes, exactly. Exactly right. Okay, well, let's stop here. If you have more questions, please come to office hours, and see you on Thursday. Thanks.